Hey there. So, you probably remember the periodic table, right? That giant, colorful chart hanging in every chemistry classroom? It looks kind of intimidating, almost like a spreadsheet you're supposed to memorize. But what if I told you that's the wrong way to look at it? What if it's actually a map? A treasure map, even, filled with secrets and a hidden code. Well, today, we're going to crack that code. So let's just jump right in. Have you ever wondered why it has that weird shape? All those blocks and gaps and funny rows at the bottom? I mean, why isn't it just a simple grid? Well, it's definitely not random. There is a single, super elegant rule that explains the whole thing. It's a master key that once you get it, makes everything else just click into place. All right, here's the game plan. First, we'll talk about the table's big secret. Then I'll give you the master key, this one concept called Zeph. We'll see how it controls an atom's size and power, and then how that shapes an element's entire personality. By the end of this, you're going to see the whole thing in a new light. So we're kicking things off with the big secret. Look, the point isn't to memorize that the stuff on the left is different from the stuff on the right. Nope. The goal is to understand why. The whole table is built on these really predictable patterns. Chemists call them trends. Our job today is to find the one single thing that causes all of them. And here we go. This is it. The master key. The one concept that explains it all. It's called effective nuclear charge, or as we'll call it, Zeph. Now, I know that sounds super technical and maybe a little intimidating, but trust me, the idea behind it is incredibly simple. And it is, without a doubt, the most important thing you need to know to make sense of this whole chart. Okay, so let's break Zeph down. Forget the fancy name for a second. Just picture the nucleus of an atom, the center, as a powerful magnet, right? And that magnet is trying to pull on the electrons way out on the edge. But there's a catch. There are other electrons closer to the center, kind of in the way. These inner electrons act like a shield, blocking some of the magnet's pull. Zeph is just the amount of pull that actually makes it through that shield to grab onto that outer electron. It's the effective charge it feels.
So how does this pull change as you move around the table? Well, think about it. As you go from left to right across what we call a period, you're adding more protons to the nucleus. That makes your magnet stronger. But, and this is key, you're not adding any more inner shells to shield it. So what happens? The net pull, ZF, gets stronger. But when you go down the table, down a group, you're not just making the magnet stronger. You're adding whole new layers of those shielding electrons. And that extra shielding is a huge deal. It more than cancels out the stronger magnets, so the actual pull felt by the outer electron gets weaker. So this is the main takeaway right here. Zeph is the magnetic pull that outer electron actually feels. Everything else, and I mean everything else, is just a consequence of this. Think of Zeph as the first domino. It falls and it knocks over all the others. Size, reactivity, you name it. It's the cause, everything else is the effect.
All right, now for the fun part, let's watch those dominoes fall. Now that we get the pull, let's see what it actually does to an atom. We're going to look at how Zeph directly controls two big things, an atom's physical size and the energy involved in playing with its electrons. First up, size. This one's kind of weird, so stick with me. As we go across a period, left to right, we just said that Zeph, that pull, gets stronger and stronger. So the nucleus is yanking on those outer electrons harder. And the result? The atom actually gets smaller. Isn't that wild? You're adding more stuff to it, but it shrinks because that central pull is just so much tighter. Going down a group, though, is the complete opposite story. For one, we know Zeph gets weaker. But on top of that, you're adding whole new shells or layers of electrons. So you've got a double whammy, a weaker pull on electrons that are already way further out from the center. The result is pretty obvious, right? The atoms get bigger, a lot bigger as you go down the table. Okay, let's switch gears to energy. It's pretty logical. If an atom has a high Zeph, it means it's got a death grip on its electrons, right? So it's going to take a ton of energy to pry one away. That's what chemists call ionization enthalpy. But that strong pull also means it's really good at grabbing a new electron that happens to float by. That's called electron gain enthalpy. So simply put, a stronger pull makes it harder to lose an electron, but way easier to gain one. And this brings us to another big idea, electronegativity. I love this one. The best way to think about it is like a chemical tug of war. When two atoms are bonded and sharing electrons, electronegativity is basically a measure of which atom pulls harder on those shared electrons. So can you guess the pattern here? I bet you can. An atom that has a really strong internal pull, a high Zeph, is of course going to be the champ at that tug of war. So yeah, just like the other trends, electronegativity goes up as you go across the table, and it goes down as you go down. See, it always comes back to Zeph. Okay, we've talked about size, pull, and power. But who cares, right? Why does this stuff matter? Well, because these tiny atomic properties are what give an element its entire personality in the real world. We can finally connect the dots and understand what actually makes a metal a metal. So, what's the one thing metals are famous for? They love to lose electrons. Okay, so which atoms are good at losing electrons? The ones that don't hold on to them very tightly. The ones with a low pull, a low Zeph, which means a low ionization enthalpy. And where are those on our map? Yep, to the left and down at the bottom. And that is exactly where you find the most metallic elements on the whole table. And nonmetals? They're the total opposite. They are desperate to gain electrons. So which atoms are the best at grabbing new electrons? You got it, the ones with the strongest pull, the highest ZF. And where are they? On the far right and up toward the top. It's a perfect mirror image. The pattern just works. And all of this leads us to chemical reactivity. Think about it. The most reactive elements are going to be the ones that are most desperate to either ditch an electron or gain one to feel stable. So you get these two hot spots on the table. Way over on the left, the alkali metals are dying to lose just one electron. And way over on the right, the halogens are dying to gain just one. And in between? Right at the very end of the row, you have the noble gases, who are perfectly happy. They're stable. They don't want to do anything, so they're not reactive at all. Okay, we've just built this entire logical system, and it all started from that one simple concept of Zeph. So let's zoom out, let's put it all together, and just admire how neatly this whole puzzle fits together. And there it is. Just look at this. It's the whole story on one slide. See that top row? Effective nuclear charge? It increases across, decreases down. Now look at everything else. Atomic radius, ionization enthalpy, metallic character. Every single one of them is a direct, logical consequence of that first row. It's beautiful, isn't it? It really is the one role that explains it all. So here's the grand takeaway. The next time you see a periodic table, don't try to memorize a bunch of different trends. Just remember Zeph. Just remember that magnetic pull. If you can remember how that changes, you can figure out everything else from scratch. You don't have to memorize it. You understand it. You've officially cracked the code. So I'm going to leave you with a little thought experiment to try out your new code-breaking skills. Imagine scientists discover a brand new element, and they place it way, way down in the bottom left corner of the table. Based on what you now know, what could you predict about it? Would it be big or small? Would it be a metal? And how insanely reactive would it be? You already know the answers. Thanks for tuning in.